So we'll be starting the last chapter of our last unit here, which is going to be on parametric equations. So we're going to go ahead and start from here and then look at some more specific types of parametric equations and really hang out on a particular type called polar equations for the rest of the class. But first we have to define what parametric equations are. So parametric equations are equations of the form x equals f of t, y equals g of t. So we're taking our coordinates of our points and we're making them into two separate functions, a function for the x coordinate, a function for the y coordinate, where t is a parameter. So given some t, we'll be plugging in t and getting out x and y. So that's the general sort of idea behind parametric equations. So again, we're plugging in t, we're getting out x and y. And so that's going to be what our function looks like. So this definition here allows us to create curves that would normally not pass the vertical line test as two functions of t. So instead of having x out and then x in, y out, where we can't have two different y's come from the same x, we can get a t now plugged in where we can end up with one x and two y's because t is going to be different values all the way through. So our points will look like f of t, g of t for some t. Graphing the curve, as it says here, will also give an orientation. So the direction in which the curve is generated as the parameter increases is the positive orientation of the curve. And so we indicate by arrows drawn on the curve. So we'll go ahead and take a look at an example of one here. So here our x's are given by this particular equation, or y's by this one. And so kind of the best way of doing this is a modified t-chart. So we'll do t values, x values, y values, and then points. And so we'll just plug in a couple of t's here and see what they end up giving us. So first off, when t is 0, we get -3. We get 4. So our point is -3, 4. When when t is 1, we plug it in here, we get 2 minus 3. We get -1. 6 plus 4, we get 10. So we get the point -1, 10. When t is 2, we get 4 minus 3, we get 1. 12 plus 4, we get 16. Then we get, let's see, 6 minus 3 is 3. 18 plus 4 is 22. And then lastly here we got 8 minus 3 is 5. And we've got 24 plus 4 is 28. So just taking a look at what our points give us here, we notice that each time we look at the next point, we're going up in x value by 2, and our y value is going up by 6. And so we can actually just sort of imagine what would happen here, that this is a consistent change in y and a consistent change in x, which would likely give us something that looks like a slope. So we're looking at something probably linear here. And so I've got 14 hash marks here. I'll go by 2s. And then we'll go by 1s here along the x-axis. So we've got the point -3, 4, -1, 10. So 2, 4, 6, 8, 10. We got 1, 16. 3, 22. So we can see that it is going to end up being linear. Then we have 5, 28. So starting at t equals 0 here, we can see that as t increases, we end up just going along this line this way. And so we would give the curve here some orientation by drawing these little arrows alongside it. So we can also continue if t was going in the negative direction as well. We would be going off that way. And so this is a way of representing a line as two different equations for x and y. We can see here that we have a slope. We just use our slope formula here. And when we do that, we get 6 over 2. So we get 3. And later on, we'll see how we can kind of just look at the equations and kind of get what our shape should be, if it's aligned, what the slope is, that kind of thing. But this is then an example of a parametric curve from t. So let's go ahead and take a look at another one here. We encounter it kind of the same way: t, x, y, and then a point. And in this case, we see that we have x is just 2t. It's rather simple. But our y actually has a square on it. So we'll go ahead and see how that makes a difference here. So we have x is going to be 2 times 0, so we just get 0. And we got 1 here. When t is 1, we've got 2. We've got 4 plus 1 is 5. 2 times 2, we get 4. And then when we plug in t here, we get 2 squared is 4, times 4 is 16, plus 1, we get 17. And then for 3, we get 6 here. 3 squared is 9, times 4, we end up with 36, plus 1, 37. And so we can see here that we have the x values going up by even numbers. And the y values look like, what's 1 squared? We've got, well, I guess it's 0 squared plus 1. We've got 2 squared plus 1. We've got 4 squared plus 1. 6 squared plus 1. And so it looks like almost like taking the x value, squaring it, and then adding 1, which is not by coincidence. Just go up by 2's again. So we've got 2, 4, 6, and so on. So we have the point 0, 1, 2, 5. We've got 4, 17. So 8, 10, 12, 14, 16, 17. Right about there. Oops. And then lastly, we have 6, 37. So you can see we have a lot more curve to this one, and that comes from having the square on our y. So it looks almost like half a parabola here if we start at t equals 0. Right, and we can imagine what happens if we let t be negative. We would end up with really the opposite part of the parabola. So this is a parametrization of a parabola. And so it might be helpful to say, since we have a line here, a parabola here, shapes we're familiar with, how can we actually get the x versus y graph? In some cases, the parameter can be eliminated from the parametric equations, giving us an equation with x and y. So we're asked to eliminate the parameter, give a new parametric representation of the curve. So the first thing we want to do is figure out how can we get rid of t and just be left with x and y. The simplest way of doing that is just to solve for t in one equation, plug it into the other. Right? If we solve for t in the x equation, plug it into the y equation, we'll end up with y equals some function of x, which is what we typically like. So when we have the option, we'll typically solve for t in the first equation here in the x equation. And so we get t equals x plus 3 over 2. We'll go ahead and plug that in. If we do that, there's a little bit of cancellation that happens here. So we'll go ahead and we cancel. We get 3 times x plus 3 plus 4. Distribute. We get 3x plus 9 plus 4. So we get y equals 3x plus 13. And that's going to be our eliminate parameter. This is what our line should be equal to, 3x plus 13, which is what we end up getting here. And it also says to give a new representation. So we have a bunch of different options that we could take here. So if we have 3x plus 13 here, the simplest route is just to say, what if x was equal to t? What happens then? Well, then y is equal to 3t plus 13. We simply swap out the x for t. Right. Likewise, we could say, well, what if y equals t? Right. In that case, we get t equals 3x plus 13. We typically would want to solve for x, though. So t minus 13 over 3 equals x. But we can make some other routes here. We have a 3x here. What if we instead replaced it with t? What if we let t equal 3x? Then y would just be equal to t plus 13. Right, so there's all kinds of options we can actually use here. So now we've kind of exhausted that. Let's go ahead and move on to the next one. In this case, if we simply take this equation and we square both sides, we end up that x squared equals 4t squared. And I see 4t squared here, so we can plug in and just get that y is equal to x squared plus 1, which is the parabola that we saw before. And likewise, we have a few different options. If we want to make a new parametrization here, say we let maybe t equal x squared, right? Then x would be root t. And in that case, we would have our y equal to just t plus 1. So that's one option. Another option, maybe we want just x equals t again. So y equals t squared plus 1. So that's more than we were asked for. So in general, if we have, especially this kind of group of things, notice that in the linear case, we had number times t, plus or minus a constant. So number times t plus or minus a constant. That's going to be part of our line. It's always going to be a line. So a parametric equation for a line looks like that. We're going to have whatever our x will be equal to some sort of constant plus a times t, where a is also a real number here. And it's going to be part of the slope. And y would be constant plus b times t. And so that's a line with slope b over a. So we take the coefficient of t from the y part, we put it over the coefficient of t in the x part. And it'll also pass through the point x sub 0, y sub 0. If we let t equal 0, then we get x is x sub 0, y is y sub 0. All right, so we can generalize and say that that's always true. Right, so now we'll go ahead and kind of make things a little bit more complicated. We'll kind of start injecting some trig into our parametric equations here. So we'll set up the same way. And we'll think about what are some nice things that I would like to get in there. Well, I have 2 pi there already, so really any integer is going to be nice. If I'm thinking about the unit circle, right, I want everything between 0 and 2 pi, which in this case would be where t is 1. Right, I think about graphing cosine maybe. I would like to get maybe pi halves. So in that case, if I plug in t equals 1/4, right? If I plug in 1/2, I get the pi angle in there, and then 3/4 will give me 3 pi halves. Right, so if I plug in first off 0, cosine of 0 is 1 times 3 is 3. Sine of 0 is 0. And so likewise, I should get the same thing for the last entry there. At 1/4, that gives me cosine of pi halves, which is 0. And the sine of pi halves is going to be 1 times 3 is 3. 1/2 here, I plug that in, I get pi as my angle. Cosine there is negative, so I get -3, 0. And then likewise, when I plug in 3/4, I get 3 pi halves on the inside. I get 0, -3. So if I were to graph that, I end up with the first point is at 3, 0, then 0, 3, negative 3, 0, 0, negative 3, and then I actually go back to the beginning. So when I graph this, if I haven't done a poor job, it should look like a circle of radius 3. And I do want to indicate the orientation. And I'll go ahead and put some arrows on to indicate that orientation. And we have a similar equation here, set of equations here. And we're asked, how is it different? Well, we remember that the cosine is an even function. The sine is an odd function, and that will help us take care of the negative on the inside. That means that x should be equal to 3 cosine of 2 pi t. Right, since we have an even function, the negative goes away. And for the odd function, the negative actually comes out front. And so what will happen is we'll go ahead and set up now the same t values. And we'll find the difference here. The x's should all be the same. 3, 0, negative 3, 0, 3. The y values have opposite signs. 0, negative 3, 0, 3, 0. So when we go to graph this, we get the same points, but we get them in a different order. Right? We start at 3, 0 again. This time we go down to 0, negative 3. And then we go across to negative 3, 0, then up, then back. So when we graph this, it's the same circle of radius 3, but now our orientation is backwards. So the orientation is reversed here. And that means that these are, in fact, different graphs, because the orientation is intrinsic to the graph. So we'll start putting in some calculus now. Now we've kind of gotten a good idea for the differences between these graphs and kind of just how to make some parametric curves. Say we want to find a derivative. And for some of these parametric curves, we can't necessarily eliminate the parameter and just get y in terms of x. Right? In this case especially, this is not a function. And so if we want to get a derivative, we would have to find some alternate route. Typically in Calc 1, we would actually take this and break it into two different functions, kind of the top half, bottom half. But since we have defined things as functions of t, we can find a derivative that works for any point on this in relation to t. So if we have x is f of t, y is g of t, and f and g are both differentiable, then the slope of the line tangent to the curve at any point corresponding to t is, and we have dy over dx, right? The typical Leibniz notation of our first derivative. But we have x is related to t, y is related to t. So the way that we break that up is we have dy over dt over dx over dt, right? And if you're thinking of these as just variable quantities, the dt's would cancel. We just get dy over dx, right? dy dt, though, is g prime of t. dx dt is f prime of t. So we put the derivative of the y equation up top, the derivative of the x equation on the bottom in terms of t, and we have our derivative. That's all provided that f prime of t is not equal to 0 anywhere inside that interval. All right, so we'll go ahead and find dy over dx for the previous example there, and in particular that was talking about the circle. We had 3 cosine of 2 pi t for x, and y equals 3 times the sine of 2 pi t. So we want to find dy over dx. And so that would be y prime over x prime in terms of t. Right, and if we're looking at y prime here, or dy dt, right, then when we get 3 times, take the derivative of sine, we get cosine of 2 pi t. And then by the chain rule, we get times 2 pi. In the denominator, we get the x prime here. We take the derivative of 3 cosine 2 pi t. So we get negative 3 sine of 2 pi t. And then, of course, the chain rule times 2 pi. So the 3's cancel, the 2 pi's cancel. And so we end up with negative cosine over sine is cotangent of 2 pi t. So this is our dy over dx, our derivative here. So our t will give us any of the slopes of the line tangent to our curve at whatever t value results. All right, so that's dy over dx. Where is the tangent line horizontal to the curve? So all we have to do is set our derivative equal to 0. So we're looking for where is the cotangent of 2 pi t equal to 0. And so we know that means 2 pi t would be equal to all the angles where the cotangent is 0. Right, and that's going to be at 0, pi halves. Let's see, 3 pi halves, 5 pi halves, etc. And then in the other direction, negative pi halves, negative 3 pi halves, and so on, going the other way. Right, and we know this is then pi over 2 plus pi times n, where n is an integer. So if we solve for t, we have to divide by 2 and pi. So we divide by 2, we get pi over 4. Divide by pi, we just get 1 over 4. Plus, divide by pi, we just get 1. Divide by 2, we get 1/2 n, where n is an integer. So that's all the places where the tangent line is horizontal to the curve. So we go back up here, we see that should be at 1/4, 3/4, and so on. So 1/4, that's where x is 0, y is negative 3, or sorry, this curve. Where x is 0, y is 3, right? That's the top here. 3/4, 0, negative 3, that's the top and bottom of the circle over and over again. So that matches up with what we want here. All right, so it's relatively simple to find these derivatives. It's just a matter of putting the one for y over the one for x. So our last little bit of calculus, just for the parametric stuff in general, before we start getting into polar stuff specifically next section, is talking about the arc length for parametric curves. Right, we talked about that back in our first unit. We talked about the arc length for a particular function. In this case, we have two different functions involved, right, both in terms of t. So before we had 1 plus our derivative squared under a root, take the integral. Right? In this case, it's going to be both derivatives squared under a square root added together. All right, so our arc length is from a to b. That's t values that we're looking at. It's square root of derivative of f squared plus the derivative of g squared. And so we'll go ahead and use that right here. It says to find the circumference of a circle given by y equals r cosine of t, x equals r cosine of t, y equals r sine of t. Right, so this is going to be our typical case for a circle. X, number times cosine of an angle, y, r times sine of an angle. And so we need to figure out then, where do we start and where do we stop? Well, if we're finding the circumference of a circle, we want to go around the circle once. And we know that going around the unit circle once is going from an angle of 0 to 2 pi. Right? So then we'll go ahead and find our derivatives. Find our f prime and our g prime. Our f prime here is x prime. It's negative r sine of t. Right, we take the derivative of cosine, we get negative sine. Derivative of y, we get r cosine of t. And so we go ahead and plug this into an arc length, and that should give us our circumference. So 0 to 2 pi, root. We have to square both these guys and add them together. So negative r sine of t squared plus r cosine of t squared dt. And so you can imagine, since we're squaring and taking a square root, only very particular types of curves are actually going to work out well for us in this case. So we're going to have to be very careful on problems selected for these types of examples here. So I'll go ahead and continue here. We've got root r squared sine squared of t plus r squared cosine squared of t. This isn't something that we'd really readily be able to take an integral of at this point. It would be nice if we can kind of get the r out of the way. Since it's not related to t, we can actually eventually pull it out of the integral itself. But first we'll have to factor it out of the inside of this root. So r squared sine squared of t plus cosine squared of t. And actually this is Pythagorean identity 1. And so we just get square root of r squared. We get 0 to 2 pi of the integral of r dt. So that's RT evaluated from 0 to 2 pi.